Welcome back, everybody. In lesson 7.3, we're going to continue our look at similar geometric figures. Okay, this time focusing on similar triangles. Okay, basically in this lesson, we'll show you some shortcuts for proving triangles are similar to each other, and then also show you some applications that are unique to similar triangles. Okay, here we go. So let's start with this. Let's say I have two triangles that are different sizes, but when I take a look at the angles, it looks like all three angles are congruent to each other. So two triangles, different sizes, but all congruent angles. Well, what's true about this? Well, it looks like these triangles are the same shape. It looks like they're similar to each other. And that's going to be our first kind of shortcut, or our first postulate for the day. We'll call it the angle-angle similarity postulate. We're going to say that if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. Okay, so if I have two triangles where two angles are congruent, and I only need two out of the three angles because we know by the third angle theorem that means that the third angles are also congruent. So if that's true, we know those triangles are similar, meaning that their sides will be proportional. So let's do a couple questions where we use that angle-angle similarity postulate. Problem 1 says, are the two triangles similar? How do you know? So for A, we're given triangle RSW and triangle VSB. And let's take a look at what we're given for those triangles. Now both angles R and V measure 45 degrees. Therefore they are congruent. So we have one out of the two congruent angles that we need. And then the other thing we have here, where these two triangles come together, we have a set of vertical angles. Okay, we know that vertical angles are always congruent. So that's my second of the two angles I need. Therefore, for this question, are they congruent? We can say yes. And how do we know? By, we'll say AA squiggly, as in the angle-angle similarity postulate. If two triangles have two angles congruent, okay, the triangles are similar, all the angles are congruent, and the sides are proportional. Let's take a look at another example in part B. It says again, are the triangles similar? How do you know? So this time I'm given two triangles, and both of them have an angle measuring 70. So that'll be one out of the two congruent angles I need to say they're similar. And then notice it didn't quite give me the matching angles for the other measurements. It gave me angle J as 30, but it didn't give me the corresponding angle P. Also, it gave me angle Q on the right triangle, but not the corresponding angle K on the left. So what I can do with this one is I can figure out what those missing angles are. For angle K, since I know my other two angles, I can say it's equal to 180 minus 30 minus 70, the two angles I know. That'll give me an 80 degrees for angle K. Now that doesn't match up with angle Q up here. If I did the same thing for angle P, I'd see it doesn't match with J. So these two triangles don't have congruent angles. Therefore, no, they're not similar to each other. Okay, we know similar figures have all corresponding angles congruent. We just showed they're not in this case. So we can't use the angle-angle postulate to say they're similar. Next thing we're going to do is look at two additional shortcuts for proving triangles are similar, two additional theorems. And they're both coming directly from the angle-angle postulate we talked about a second ago. The first one is the side-angle-side similarity theorem. It says that if an angle of one triangle is congruent to an angle of a second triangle, and the sides that include the two angles are proportional, then the triangles are similar. Okay, so this is similar to our side-angle-side congruence theorem. Okay, but rather than talking about congruent sides, we're talking about proportional sides, which will make the triangle similar instead of congruent. Okay, so if I have two triangles with a set of angles congruent between the two of them, and then the sides that include those angles, or the sides that surround those angles, are proportional. So as in the ratio of AB over QR is equal to the ratio of AC over QS, then that means that the rest of the angles are congruent, the rest of the sides are proportional, or the triangles are similar. We have the same thing with the side-side-side similarity theorem. It says that if the corresponding sides of two triangles are proportional, then the triangles are similar. So again, we're not talking about two triangles with all sides congruent. We're talking about all sides proportional, as in the ratios of each of those sets of corresponding sides are equal. Well, if that's the case, we know the triangles are similar. All the angles will be congruent, and all the sides will be proportional. Let's take a look at some problems that use the side-angle-side and side-side-side similarity theorems. So problem 2, part A says, are the triangles similar? If so, write a similarity statement for the triangles. So I'm seeing two triangles here. I'm seeing the smaller triangle KLP, which is embedded inside of the larger triangle KMN. It looks like they're the same shape, but let's determine that for sure here. Now the trick for this one is I can check my side-angle-side theorem. Since both these triangles share angle K, I know I have one angle congruent. And then what we'll do is we'll check and see if the sides that include angle K, that surround angle K, are proportional. So we'll look at the ratio of KL over KM. So we have KL, right, over the longer side, KM. That's going to be equal to KL, which is 8. All right, over the longer side, KM, which will be 8 plus 2, in other words, 10. Well, what does 8 plus 8 over 10 reduce down to? Well, both those numbers divide by 2, so we can reduce that down to a 4/5. And to determine if those sides are proportional, we'll look at the bottom sides of the triangle, KP over KN. And what we'll do is we'll see if we get the same ratio, if it reduces down to the same thing, to see if it's proportional. Okay, KP is 12. We'll do that over KN, which is 12 plus 3, 15. All right, both 12 and 15 are divisible by 3. 12 divided by 3 is 4. 15 divided by 3 is 5. Okay, we get that same 4/5 ratio for both those sets of sides. Therefore, we'd say they are proportional. So what I have here then are two triangles with an angle between two proportional sides. So the answer for this one is I can say yes, triangle will go KLP is similar to triangle. Then in the same order, we'll say KMN by SAS squiggly line, as in the side-angle-side similarity theorem. Let's take a look at another example in part B. Again, are the triangles similar? If so, write the similarity statement. So I have two triangles here. And now notice this time I'm not given any information about the angles or how they relate. But I am given all three sets of sides. So what I can do with this one is check and see if all three sets of sides are proportional. And if so, we can say they're similar based on the side-side-side similarity theorem. So let's go ahead and do that. We'll look at the ratio of, I'll start with the smaller sides, 6 over 9. Okay, 6 over 9 is going to reduce down to 2/3. And what I need to do now is see if the other sides reduce to 2/3 as well. Let's go with the medium length side next, 8 over 12. Both 8 and 12 are divisible by 4. That'll reduce to 2/3 as well. And same thing with the last set of sides, the 10 and the 15. Both 10 and 15 are divisible by 5, so if I divide, I'll get 2/3 also. So I've just shown that all three sets of sides are proportional. Therefore, I can say yes, triangle, let's go UTS, is similar to triangle. Then staying in the same order, we want to start with the smallest angle across from the smallest side, so we'll go with W. Then we went right angle looking angle, so we'll go WVX. And we can say by SSS similarity. Next thing we're going to do is get into some practical applications of similar triangles. And they're going to involve making something called indirect measurements. I'm saying indirect measurement is a way of measuring objects that are difficult to measure directly. So rather than laying the tape measure up to the object, we'll use proportions and similarity to figure out its length. Okay, that's the indirect measurement idea. All right, so for example, problem 3 part A says, before rock climbing, Darius wants to know how high he will climb. He places a mirror on the ground and walks backwards until he can see the top of the cliff in the mirror. We want to know what's the height of the cliff. Okay, so we have a cliff to climb, and it would probably be nice to know if it's 30 feet tall, 100 feet tall, 1,000 feet tall before we get climbing it. We're going to say this is an indirect measurement because I'm not going to climb to the top of the cliff and drop a tape measure down. What I'm going to do instead is set up proportions to figure out how big it is. Okay, so the trick I'm going to do is I'm going to stand right here, put a mirror on the ground, and stand in a position where I can see the very top of the cliff in the mirror. Now the physics trick we have there is that the angle of reflection from your eyes, okay, to what you're looking at in the mirror is going to be congruent on both sides here. And then also, since we're assuming that both the cliff and the person measuring are coming out of the ground at a right angle, what we have are two triangles with two angles congruent. So by the angle-angle similarity postulate, we know these triangles are similar. Okay, what I can do then is I can make some direct measurements of stuff that's easy to measure. Let's say our eye level is 5.5 feet above the ground, and we're standing from 6 feet away from the mirror. Easy to measure. We can then measure along the ground to the cliff from the mirror, which is 34 feet. Okay, it's not difficult to measure along the ground. And what I can do with that information is I can set up a proportion. I can say 5.5 over 6 is equal to the height x over 34. And then when I cross multiply and divide, we'll end up with our height of the cliff. Okay, cross multiply, 6 times x is 6x is equal to 34 times 5.5, which would be a 187. We'll divide both sides by 6, and we end up with x is equal to 31.2 feet, we can say. Okay, so neat little trick. We can use a simple tape measure and a mirror to figure out how high the cliff is. All right, let's show you one more indirect measurement example. And this one's going to use basically a tape measure and just shadows to figure out heights. In part B, it says, in a garden, a bird bath that is 2.5 foot tall casts a 1.5 foot shadow. At the same time, an oak tree casts a 90-foot shadow. We want to know how tall is the tree. Okay, it'd be nice to have a picture for the situation, so let's draw one out. Let's say we have a oak tree. Let's say that's what oak trees look like. Okay, we're not sure how tall, but we know it casts we'll shade that a little bit better here, 90-foot long shadow. And at the same time of day, we have a bird bath, which is 2.5 feet tall, casting a 1.5 foot shadow. And that's all we need to know to figure out how tall this tree is. Okay, the trick that's happening here is it's the sun that's making those shadows happen. Okay, it's the sun hitting the top of both our shapes, going to the ground. That's going to make the shadows. And when I do that, what I end up with are triangles. Just like the last problem, we'll assume these are both right triangles. And then also, since I'm doing my measurements at the same time of day, basically within the same yard, I know my angle of elevation to the sun is going to be congruent for both these triangles. So once again, by the angle similarity postulate, I have similar triangles. I can use that to set up proportions and solve. All right, so I'm going to set this up the way I see it. X over 90 is equal to 2.5 over 1.5. Okay, cross multiply, we have x times 1.5, we can say is 1.5x. Do 90 times 2.5, which will give us a 225. And then divide both sides by 1.5. And we end up with x equals 150. So in other words, 150 feet tall. Okay, nice direct measurement problem. It's going to be a lot easier doing that, measuring shadows, than it is climbing to the actual top of that tree and throwing a tape measure down. All right, so that's it for lesson 7.3, similar triangles, okay, with some more nice applications. Like usual, start going to town on the homework, get your practice in. Let us know if you need any help, and we'll see you next time around.